Hello everyone. In the today's video's lecture, we discuss about emitter bias common emitter amplifier circuit. Okay, so again the same common emitter circuit with the emitter bias. So we will consider this circuit where you have the resistance Re along with Rb and Rc as we discussed in the previous fixed bias circuit. So the procedure is first to short all the DC supply and short all the capacitance, and corresponding to this is the modified circuit. This is the step 2, this is the step 1. Okay, and now step 3, you have to draw the small signal model for this circuit. So to draw the small signal model for this, I will draw it only for the transistor initially. So this is emitter, this is R0, this is beta IB, okay, and this is base, and this is my input current IB. Fine, yeah. So this is my small signal model for the transistor only, where you have three terminals: collector, base and emitter. So now along with this you have the other two components, which is three components: RB, RE and RC. So here you see that RB is connected from base terminal to ground. So here we have this RB connected from base terminal to ground, and RE from emitter terminal to ground. RE from emitter terminal to ground. Okay, and you have the RC from collector terminal to ground. So you have RC from collector terminal to ground. This is my RC, RE, and this is my RB. Okay, so this is the complete model of the small signal model of the given emitter bias common emitter amplifier circuit, right? So in this, to do the AC analysis, this is my input V in, this is plus and this is minus, and this is my output V0 plus and minus. Okay, corresponding to this is my input current and this is my output current I0. Okay, so now to find out the input impedance Zin, as per the definition, input impedance is the impedance seen with respect to input voltage and input current. Okay, so input voltage means it is between these two terminals. So now whenever you want to find the impedance between any two terminal, what is the procedure? All the voltage sources has to be shorted and all the current source has to be open. So with this you will be having only this part of the circuit, because what happens here, the current source will be open and R0 will be again infinite, it will be an open circuit. So RC here will become 0 because you are shorting the output voltage V0 whenever you are calculating the input impedance. Okay, so it is actually the impedance seen between these two terminal input voltage. Okay, so that we see it here as RB is one resistance component, and another resistance component we see between this base terminal and the reference. We call this as ZB for our analysis as of now. Okay, so first we will have to mention this Zin is equal to RB parallel with ZB. ZB is nothing but the impedance seen between these two terminal. Okay, so what is ZB? The impedance seen between these two terminal. The voltage between these same two terminal is nothing but your input voltage. So input voltage and the current entering due to this ZB is IB. IB is the current that is entering due to this input voltage V in. Okay, so now what happens, this ZB is nothing but, if you apply this KVL to this loop, Okay, so this I will write this part as modified circuit. So this is and this is this. Okay, so this is V in, the voltage between the ZB what I told from base to ground. Okay, and this is beta Re, and this is what, this is Re. Okay, so I have just written the only ZB part what I am analyzing here. Okay, so now the current flowing through the beta Re is Ib, whereas here it is Ie. The current here is Ie. Okay, so I will apply KVL to this loop. So V in is Ib into beta Re plus Ie into Re. Okay, so now this is Ib into beta Re plus Ie is 1 plus beta times of Ib these are all small b because it is the biased signal Re. Okay, so now approximating this 1 plus beta as beta itself, so Ib into beta Re plus beta into Ib into Re. So taking Ib common, I can take beta also common, so Re plus capital Re. So this is my input voltage corresponding to this network what I have taken. So now to substitute it for ZB, which is my V in by Ib is equal to beta times of Re plus Re. So this is the value of my ZB, which is the impedance between the base and the reference. So my input impedance will be RB parallel with beta times Re plus Re. So this is my input impedance. Okay, so now to find the output impedance, that is seen with respect to output terminal here and here, fine. So Z0 output impedance is nothing but V0 by I0 with respect to these two terminal. So whenever you want to find the impedance between any two terminal, all the voltage source are shorted and the current source are open circuit. So when you short the input voltage, this RB becomes 0 and beta Re will also becomes 0. Okay, so now what you have on the other side is, so the R0, this is anyhow open circuit. If you think IC is flowing here and it is the same IC is also flowing here, so it becomes RC parallel with R0 plus RE. Since R0 is very large, so RC parallel with large value R0 or infinite. So this is R0 is large, I will take it theoretically infinite. So infinite plus finite value, it will be again infinite. RC parallel with infinite, Z0 is again approximately equal to RC. So this is the output impedance of the circuit. Okay. So now finding out the gain expression. I will take it in the next. Once again I have to redraw the circuit. So this is my RB, this is my R0, this is base, emitter, collector, and this is RC, right? So now we are finding the gain of the amplifier circuit, AV, okay, which is nothing but output voltage by input voltage. Okay, so now for this we will consider the output voltage, which is equal to I naught into Z naught. Z naught is anyhow RC, we have approximated that, and I naught is nothing but this is I naught and this is IC, which is beta times of IB. So here what we have here is minus IC into RC, because Z naught is my RC. IC is nothing but beta times of IB into RC. Okay, so this is my V naught. So in the previous slide we see that my IB is nothing but from this equation we get, so this equation I will just rewrite it. IB is V in by ZB. So from this equation, from the previous, we got that ZB is equal to V in by IB. So this we write it as IB is equal to V in by ZB, and ZB we got it as beta times of RE plus RE. This is my IB. Substituting here beta into V in by beta times of RE plus RE into this RC as it is. Beta and beta cancel. Taking V into the denominator, V naught by V in is minus RC by RE plus RE. So this is the expression of the voltage gain for the fixed bias amplifier circuit. That is, you see here, this is the fixed bias, that is, sorry, the emitter bias, not fixed bias. Emitter bias, you have an RE resistance connected to the emitter, so that has an additional effect for this biasing the circuit. Okay, so it is emitter bias, common emitter amplifier circuit, for which you will get the input impedance as beta times of RE plus RE parallel with RB, output impedance as RC, and the voltage gain is minus RC by RE plus RE. Okay, and the current gain AI is nothing but IC by IB, which is equal to beta. This itself will be your current gain. Okay, so now compared to the fixed bias what we discussed in the previous class. Okay, so this is the fixed bias, you see here. So the input impedance was RB parallel with beta RE. So here the input impedance has been increased by some factor RE, capital RE, that is the emitter resistance what you got addition. The output impedance remains same as RC, whereas the gain expression what you had here is minus RC by RE, whereas with the emitter bias you have RC by RE plus RE. Okay, and the current gain is same, only the gain and the input impedance has been changed. The input impedance has increased by factor capital RE, that is emitter resistance, and the gain has been reduced by the RE, the capital RE, which is the emitter resistance, which you can see here. This is your voltage gain for the emitter bias common emitter amplifier circuit, RC by RE plus RE, right? So if you want to continue with the same, the numericals for the same circuit, if you take, so the output impedance will not change anyhow, so that will remain as RC. So this is 242.2K, and RE I will take it as 0.5K in this example. In this example, RE I will take it as 0.5K. So my Zin is RB parallel with beta times of RE plus RE, and I need to calculate RE over here. So now for that I need to find out what is the IE for this circuit. Okay, so now applying the KVL for this input loop, I will redraw this circuit once again here. So this is RB, this is RE, this is VCC. Okay, so applying KVL for this input loop, I will get it as, I will write the modified circuit here itself, minus VCC as RB and VBE and this one. Okay, so this is VCC, RB, VBE and you have RE over here. So applying KVL for this loop, you have VCC is equal to IB into RB plus VBE plus IE into RE. Okay, so here I need an expression for IB, so this is IB into RB plus VBE plus this 1 plus beta times of IB into RE. So VCC, I will take the expression for IB, which is equal to VCC minus VBE divided by RB plus 1 plus beta times of RE. So taking the same example here, which was 12 volts, 12 240 and 0.5k, 12 240k and this is 0.5k, 12 minus 0.7 divided by 240k minus beta itself 51, 52 times of 0.5k. Okay, so solving this, you will get 10.3 divided by 240k, 52 into 5, 25k. So 25 plus 240, 275k. Minus 25 to 30, 215k, which will be equal to around 10 divided by 215, 46 micro, again 46.5 micro. So it will be same. So IC will be beta times of IB, which is approximately 2.4 milli. So your RE will be same, that is 26 milli by 2.4 milli, which is 10.8. Okay, so this Zin will be Zin is RB parallel with beta times of RE plus RE. RB is 240k parallel with 51 into RE is 10 plus RE is 0.5k or 500 ohms. Okay, Zin is approximately 240k parallel with 510 into 51, 2550 0 parallel 25k, approximately 25k. So Zin will be approximately equal to 25k Okay, so just approximation value, and ZC will remain same as 2.2k, which is equal to RC, and the gain, which was RC by RE for fixed bias, now for the emitter bias it is RC by RE plus RE. So it was minus 2.2k by RE was 10 earlier, now it is 10 plus 500. So 2200 divided by 510 is 54, 4 point something, 4.1 or 4.2. Okay, you see here the gain has reduced drastically from 203 here, 203 to minus 203 to minus 4, just minus 4. The gain has reduced a lot. Okay, this is the effect of the emitter bias configuration. Fine. So thank you. We will continue again in the next class.